This week we're going to study Chapter 2, Getting to Know Your Data. We will be able to cover data objects, attribute types, basic statistic descriptions of data, ideas behind hypothesis testing, and we're going to introduce a set of methods to measure data similarity and dissimilarity, and those are fairly fundamental to data mining tasks. But we will not be able to actually look at the data visualization. We're going to look at data visualization next week. For every week, I actually create a set of learning objectives. Please know that those learning objectives are actually the things that you want to check against your learning to see if you really truly has grasped those concepts and the ideas. So every lecture, I hope after the exercise, you will come back and look at those learning objectives and see if you have really met those goals. So they're not given here just for the look. Please do check. If you have any questions, post them. So next we're going to talk about data objects and attribute types. Types of data sets. Lots of data sets can be used for data mining tasks. And here we put them into a set of 4 categories. The most common one are records. Relational database holds lots of those records. Data matrix, that you can actually took as a lot of tables that we're going to actually look at in our R exercise. Document data, so those are text, descriptions, news reports, your books, journal articles, those are all document data, and they can actually be converted into a matrix format. For example, in this case, we represent 3 documents, document 1, 2, 3, and the columns represent all the words that appeared in document. We call them vocabulary. So this is the vocabulary that this data set covers. And here in the data cell, what we have, it could be the count, frequency of certain term appear in a document. It could also be other measurements, for example, TF, IDF measures that measure how important this word is in representing the content for a document. So once document data is converted in this format, a data matrix format, there's lots of mining tasks can be performed, or machine learning tasks can be performed on this representation. And the transaction data, last week we mentioned those. So in one transaction, how many items being sold? And those are also records that can be mined. We look at examples last week. We can do shopping cart mining, right? We can see how different products are bought together. Second type of data set is graph and networks. They often require a different methods to mine. And in this class, we're actually going to, although we're not going to specifically look at how to mine World Web or social networks or molecular structures, but we will actually look at how the graph data can be mined when we talk about clustering. So World Web is a network. The links among pages create a network of web pages. Social network, we probably by now we're all getting familiar with those. That people are joining into different social media. They tweet to different people. All those relations create networks, and we combine those to find how information are distributed, how messages got propagated through this social network. There are also other type of information networks, for example, citation network. I cite this person's article and somebody else cite me. By study citation network, we can see how influential every researchers are, and we can even show how influential a certain research area is and the growth over time of different research areas. Molecular structures, obviously this is a very active and very important area. To mine those, we will be able to tell what gene sequence might create different proteins and might affect people's health. The ordered data sets is also active and heavily being studied. Video data represents a sequence of images. Time series data and other sequential data. We look at transaction sequence last week. After you buy computer, you buy software, right? Those kind of patterns. Genetic sequence data, DNA sequence, those are also targets for different mining tasks. There are also spatial media and multimedia data. In this class, our focus is actually the first group. We touch upon and look at some of the graphic, some of the methods graphic algorithm can be used to identify clusters. The rest of the data types are considered more advanced and more specialized. This won't be covered in this class, as this class is your first introduction to data mining. So you will be able to learn those advanced topics in some other classes. So now we have a general idea what kind of data can be mined, and now we can look at the data objects themselves. So thinking about those records, right? You're thinking about those matrices. You have data objects in this. So you have a large table, and the data the table is made up of data objects. Data objects represent an entity. It's also called an observation. Some examples in your sales data set, you might have your observation as customers. You could have your observation as items that you're selling. And you could also have records that show a sale, a transaction. In a university database, obviously, we're all familiar. You could have your observations can be students, professors, courses, student activities, anything that's of interest that you have a question that you want to answer through the data could be a data objects. Data objects are also called samples, examples, instances, data points, objects, and tuples under different context. When you read articles, recent research, you will be able to recognize those within their context. It should not be that difficult. Data objects alone won't be any interest to us, right? Knowing this person, there is such a person does not help us. Those data objects need to be described by attributes. And the attributes is the key. It's the meat. It's actually the source of data that the data mining task will be performed in order to understand a certain phenomena. So we're going to have slides to talk about attributes later. So to match up our vocabularies, we talk about data objects. Those typically are represented in the rows in a matrix or in your relational database tables. Columns holds the attributes. So if we look at our example here, this is our rows. Our objects are documents, and our attributes are terms, words inside those documents. This is a different way. This is not represented in a table format. This is transaction data where you have a transaction ID and then a whole list of items listed here. Those are the items that one customer bought together. So one transaction ID covers a number of different items. This specific data format will be used in association rule mining. This, as you can tell, it's different. Those are not represented by attributes, but instead by the items that's made up of one transaction. So we talk about the data sets holds different data objects. What I want to emphasize at this point is the fitness of a data set for your mining task. So to select or to create a data set for a mining task, you want obviously two very important characteristics. You want the data set to be representative of the population that you want to study. The data set will always be limited. It's not going to be infinite. It covers everything you want to study. When within this limited set of data set, you want your data objects actually are representative to the population. The second properties is that the attributes we mentioned earlier. The attributes need is actually the meat for the data mining task. That's the source of information that we can mine knowledge from. Therefore, the attributes need to be as comprehensive as possible. So I'm going to actually give you some examples to illustrate those two characteristics that you want your data set to have. There was actually a very large scale study that study in the World War II. They want to know what part of the aircraft are most likely to be damaged in a combat situation. So they collect all the aircrafts that returned to the base and check which area has been damaged. Obviously, you will see this sample. In order to study what aircraft has been, which part of the aircraft are easiest damaged, you collect the returned aircraft. That's not a representative set. Aircraft that's not returned, that has been shot down, never returned, really is the ones that you want to study. Aircraft that were able to return, the damage are not that bad, right? They can return. So that's a wrong set of the data that you collect in order to investigate that problem. This example is not what I made up. It's a real study, okay? The second example is also real. This one identifies tanks. So the tanks are all camouflaged, right? To identify tanks in forest is a hard task. So people developed machine learning algorithms. They took images of tanks in forest, and then they developed a machine learning algorithm to identify forest with tanks and the forest without tanks. So this is a binary classification problem. The algorithm tested on their tested data worked almost 100% correct, like 98% precision recall. However, then when they deployed this algorithm in real settings, the performance is almost as low as random. So why was the problem? What caused the problem? It turns out that when they collected their sample, their training examples, they took pictures of tanks in forest in a rainy day. So majority of the pictures that they learned have raindrops. The algorithm learned to identify raindrops in the image rather than tanks. So this is another example that your training example is not representative of your population. Therefore, you will not be able to learn what you really wanted to learn. The second characteristic, comprehensiveness. It's not actually easy to know that some important attributes are missing from your data set. Sometimes it's easier. My first example illustrate that. So in order to answer which country is the most militarized country, you can count how many soldiers is in one country. How many soldiers in US, how many soldiers in China. You will see that Chinese has way more soldiers. However, if you take into account of general population, how many people are in China, you will see the Chinese soldier and population actually ranked 124th in the entire world, and US ranks the 8th. So that adding the attribute of the population will modify your conclusion. In some other cases, it's not very clear what attributes we need to have. We don't actually understand the problem well enough to know what attributes we need to collect. Those are the most challenging and hard to solve problem. This requires you to be familiar with the domain and understand the problem thoroughly. So body height and total earning, does that have a relation? If you want to study who earns more, should you collect body height as one of your attribute? Research shown that body height, if you click on this link, you will see, I think it says 1 inch higher will put you at the advantage of earning some thousands of dollars more than people who is 1 inch shorter than you. So we need to understand the problem to see, well, total earning does has a relation with body height. Therefore, when we study total earning, we need to collect this attribute, body height. Okay, so in conclusion, not every dataset is fit for a mining task. The dataset that I'm going to use for this class as in-class demonstration is the police shooting data that collected by Washington Post in the past, I think, 5 years. This dataset does not collect all the information there is to study police shooting in phenomena. When we get to that, we will pointing out different places. You will see yourself. You're probably also going to recognize some of the key attributes that's not included. However, the dataset has a combination of different data types that's suitable for my demonstration in this class. But it also does offer some useful information for us to understand police shooting phenomena. Okay, so now we can move on to the next slides. We're going to talk about attributes. So we mentioned a dataset holds a large number of data objects, and the objects are described using attributes. Again, attributes are called dimensions, features, variables under different contexts. So keep your eyes open and see how those terms are used in the research articles that you might read. So those attributes describe the data object, and those features are what we're going to mine. After mining those attributes, we will be able to get insights. One data objects are often described by more than one attribute. So those attributes form a vector of attributes, which is called attribute vector or feature vector. And the attributes actually holds the real data values, right? And the data values are of different types. Those are very fundamental. We have to understand this data types in order to perform any statistical analysis and a lot of data mining tasks. So there are multiple ways to categorize data types. And one way to look at it is to divide all the attributes or data into two groups. One is categorical, another is numerical. So categorical data are really qualitative data. Those are names, nominal data, binary data, yes or no answers. Ordinal data, scaled, between 1 to 5, how much do you like this car, for example? Those are ordinal data. Numerical data are quantitative data, so they're numbers. Under this group, we have interval scaled and ratio scaled data. We're going to go through those one by one. So attribute type qualitative, so remember those are categorical data. It has three subtypes: nominal, binary, and ordinal. Nominal means names, so it's name of things. For example, color, different states, different job title, ID numbers, zip codes. Zip codes, although they looks like they make up numbers, but really those numbers mean nothing. It is just a symbol that represents one location. So it is still a nominal type of data. Binary data only have two values. So binary data is a subgroup of nominal attributes that only have two states, 1 or 0. That could represent true and false, yes and no. So anything that's represented, I can only take two values. Those are binary type of attributes. Within binary type of attributes, we actually have there are symmetric binary values and asymmetric binary values. This symmetrical or asymmetrical is defined by whether we care about these two states equally or not. So one good example of symmetric binary, gender. Well, I know I'm old school, okay? So this example does not cover the current situation. Biological gender. Let's make it more. Okay. So if we consider only biological gender, male and female, and in this case we have two values, so it's binary attribute. And this binary attributes, when we calculate those, thinking about, what's the gender representation in STEM career, both gender are equally important. We care about male employee and female employee the same. They are equally important. So those are binary, symmetrical binary values. We care about two values equally. In the contrast to asymmetric binary is that the outcome, whether it's 0 or 1, it's not equally important to our mining tasks. Okay? So for example, medical test. In a population, even though we have large number of diseases possible, majority of the people will only have very few number of diseases compared to all possible diseases there is. So in order to compare patients, whether this patient is similar to another patient, the test result, whether it's positive or negative, play a different role, because vast majority of the people going to have negative test in majority of the diseases, because we don't have majority diseases. I don't have this disease does not make me similar to another person who also does not have the disease. So therefore, the negative value, the 0 value, is less important in our mining task in order to find the similar patient. Only the positive result. If I'm tested positive with COVID, then I'm more similar to another person who's also tested positive with COVID, right? So the outcome of 1 is much more important in order to identify similar patient profile based on what conditions they have. So therefore, in this case, the medical test outcome for the mining task of finding similar patients with similar health profile is asymmetrical binary. So asymmetrical binary is defined according to this task, mining task, to find people with similar health profile. I would value positive test way more than those negative tests. I don't have a real disease, and you don't have that real disease does not make us more similar, because vast majority of the population does not have that rare disease. Okay, so this is an important point. If you have questions, this is not clear, please do post a question in discussion forum. Then the third type in qualitative data is ordinal. Ordinal data is the value, a set of values that has a meaningful order, but the magnitude between successive values is not defined. So for example, size, we can rank the size as small, medium, large. So we know medium is larger than small, large is larger than medium, but we don't know whether the difference between medium and small is exactly the same as the difference between large and medium. So the magnitude between the successive values is not defined. We don't know. There's not a way to measure it. Those ordinal data are very heavily used in lots of social surveys, where people ask you to rate how much you agree with this statement, how much you like this candidate. In some medical interview, you also the doctor asks you between the scale 1 to 10 how hurt this condition is to you, the painfulness of this injury, for example. So those are ordinal data. So next we're going to look at a quantitative. So quantitative has two subgroups. One is interval, another is ratio. When they have those numerical values, we know that the magnitude between two successive values is the same. We know the difference between 2 and 1 is the same as the difference between 3 and 2, right? So those are the quantitative data. Interval data fulfills that the characteristic that we just talked about. It's measured on a scale of equal-sized unit. So 1, 2, 3, 4, 5, the difference between each of this data point is the same. The difference is 1. So we know that size, the difference, the interval is equal. But the difference between interval and ratio is that the interval data does not have a true 0 point. I'm going to use the temperature to show that, to explain what does that. This does not really happens. I mean, in our everyday life, we don't care in majority of the cases whether the data set is interval or ratio. However, it doesn't make a difference in certain statistical analysis. When some statistical analysis only works with ratio data, then you cannot just blindly convert interval, divide one interval with another interval to get a ratio. That ratio is not real ratio scale. So we're going to explain what really is the ratio scale. The difference between interval and ratio is that the interval does not have a absolute 0 point, but ratio data do. Ratio data requires a inherent 0 point. They all share the same characteristic, that the intervals between two values are the same in both interval and ratio cases. So now let me try to explain what 0 point is. So using temperature, We know temperature can be measured in at least 3 different ways that's known to me. Okay, Kelvin. Kelvin temperature is a physical temperature that measures when the particles within an object stopped moving. So this is the absolute zero point. So this is one way to measure temperature. But in our everyday life, we use Fahrenheit and Celsius, right? And we know Fahrenheit and Celsius are not the same. So we have 0 degrees Celsius. This is 32 degree Fahrenheit. So Fahrenheit 0 going to be somewhere here. So Fahrenheit and Celsius and the Fahrenheit have different scales. And their 0 point are conveniently defined. It is not linked to the physical characteristic of something. Imagine that you said we used Celsius and Fahrenheit. I can certainly define a home degree temperature like H, right? That convenience, right? Even nobody's using mine, I can still define that. Because those Fahrenheit and Celsius, those degrees are not absolute zero, we cannot say that temperature at 20 degree is actually twice of the temperature of 10 degree. Because the difference here, depending on what you measure with, use Celsius or the Fahrenheit, you're going to have different values. If we use the absolute zero, we can see clearly that the temperature at 20 degrees is not twice of the temperature of 10 Celsius degree. So what I'm saying is you can use 20 to divide 10 and receive a number of 2.0, but that is not a ratio value because you don't have an absolute point. Your 0 point is arbitrary, that defined by certain culture. Okay, then different culture could use a different way to define that 0, and they're going to have a different, the same temperature going to be measured at a different value using Celsius and Fahrenheit. Therefore, you don't have a fixed ratio. Therefore, your data, by dividing this 20 with this 10, you don't get a real ratio data. You have to have a zero, absolute 0 point, that you have physical or any other strong scientific explanation that this is the absolute 0 degree to actually have ratio data. So coming back to this slide, temperatures measured in Celsius or Fahrenheit are not ratio data. They are only interval data. And the temperature measured in Kelvin is ratio data. It's ratio scale data, and it's also interval data. Okay. So now putting all those 4 things together, we can see that all ratio attributes are also interval attributes. All interval attributes are also ordinal attributes. All ordinal attributes are also nominal attributes. You can see that the requirements is more and more stricter climbing up this scale. All the ordinal data are nominal because not only they can be identified, the values can be identified by the name, but also the sequence matters, that we know when the value, the relation between a later value and the previous value is ordered. There is an order in the data. And in interval, that or not only we have an order, we know the interval between any 2 consecutive numbers are exactly the same. So those are the interval data. Ratio data are not only interval, but also they have an absolute 0 point. Okay. So in data mining tasks, we often use another way to get the attribute types. You will see in our documentations, many methods, they will say that this method requires discrete attributes, or this method's algorithm requires continuous attributes. And discrete attributes can be predicted using classification methods, and the continuous attributes have to be predicted using regression methods. For example, linear regression to predict how much rain we're going to get in the summer. So discrete attributes covers what? Nominal values are discrete, ordinal are discrete, even some interval can also be discrete. So the key difference between discrete attribute and continuous attribute is the number of values in between two values, how many there can be. So for discrete attribute, there is a limited number of values in between any two values. For example, integer age. Between 1 and 5, you can only fit in 2, 3, and 4, no more. Okay, so the values are distinct and separate, therefore it's countable. When you have an interval, you can count how many there is. Even though the count may not be, you can't reach the last point, for example, the integer values. We don't know which number is the largest, but we know they're countable. That between two values, there is a fixed number of values in between. So those are discrete attributes. Continuous attributes, on the other hand, there is infinite possible values in between any two continuous attributes. For example, if my height is 1.50 meters and your height is 1.60 meters, how many values can we fit in between of those two continuous values? Infinite, because we can also increase the precision and make infinite number of numbers in between these two values. So therefore, continuous attributes are typically represented as floating point variables, 2.5, 2.53, 2.5346. So yeah, this is also heavily used in data mining tasks, discrete attributes and continuous attributes. Everything we talked about in this class, you have to really remember all of those and understand that. Okay, this video is already too long. I'm going to cut it, stop it here and start a new video on the next topic.